right, what acts as the centripetal force in an unbanked corner? What holds you or allows you to turn an unbanked corner? John?
Friction.
Friction. Okay, so that means right off the bat we know this. The force centripetal is being provided by and is thus equal to the force of friction. That's how all unbanked corner problems start. Okay, the rest of our givens are mass, 1,500 kilograms, radius, 40.0 meters, okay, and mu, 0.60. All right, so we've got those numbers, okay? We can plug in our formulas here. Fc is mv squared over r. Force of friction is mu times the normal force, but since it's a level unbanked corner, normal force is equal to the force of? That's it. Force normal is equal to the force of? In this situation?
Gravity.
Right. Okay, so I'm just going to write in m times g. All right, so we are trying to solve for v. So we're going to multiply both sides by r. We're going to divide both sides by m. That'll cancel. And then we'll square root in order to get v and not v squared. So v will equal the square root of 0.60 times 9.81 times 40.0 meters. Forgot to start my calculator. Okay, so we are going to take the square root of 0.6 times 9.81 times 40. So, maximum speed that that car could negotiate that corner at will be 15 meters per second. Okay? All unbanked corner questions are like that. Fc equals the force of friction, you just have to manipulate and solve. Okay, it's just algebra basically, if you can remember that you need to set Fc equal to Ff for an unbanked corner. Okay, any questions on that one? Okay. All right, let's have you guys try 1 and 2 here. I'm just going to make that bigger so you can read it a little better. Okay, I love that whoever wrote this question was an Oilers fan. But you'll find that it's not Connor McDavid, because it's really slow. Probably Corey Perry. Who's awesome, but old and slow. Both of these are unbanked corners. Okay, first one, we know the mass, 100 kilograms. We know the radius, 7.17. We know the coefficient of friction, so it's exactly like the one we just did. Okay, we've got mv squared over r, Fc, equals mu times m times g, okay, the force of friction, and we are trying to find the speed. Okay, so we're just going to bring r over, m's going to cancel, we're going to square root, okay, and plug in our numbers. So square root of 0.80, okay, times 9.81 times the radius, which was 7.17, okay, and we should get, I think it comes up to 7.5 meters per second. Okay, that is definitely not Connor McDavid, okay, because that dude is super fast, okay. He gets ahead of steam, watch out. So, kind of slow. Now, does that coefficient of friction seem kind of high for ice? Right? Like if you're skating straight on the ice, you slide pretty easily, right? But this is a question about turning.
All right? In order to turn on skates, you have to tilt the skate so you get the sharp edges of the skate to cut into the ice. All right? If you're turning really hard, that means that your skate is going to slide a little bit along the ice, okay, cutting through, and that edge is going to bite. That actually creates a very high coefficient of friction. Okay? It's how you can stop as well. Okay? If you're going to stop on the ice, you just tilt your skates, right? Lean them a little bit so the edges cut into the ice and catch, and creates a much higher friction situation than when you're skating straight on the edges. That's very low friction because you're not cutting at all. All right, so very different from when you turn to when you are like skating straight. It's why you want to have sharp skates. If your skates are not sharp, it's very hard to get that high friction situation where you can push, okay, and turn and accelerate and stop. Okay, it's very hard to do that with dull skates. All right. And then for question number 2, we have the automotive manufacturers testing the handling ability. Okay, we're looking this time for the coefficient of friction. It's still an unbanked corner, so this is still true. We got mv squared over r, mu times m times g. Okay, and this time we're just looking for r. So we're going to multiply both sides by r and then bring everything else over. Okay, so the m's are going to cancel and we're going to have v squared over mu times g equals r. So we'll take our 95 kilometers per hour, which obviously we have to convert to meters per second, okay, to be 26.4. We'll just keep all of the decimals there. Okay, so 26.4 squared, okay, divided by, we're looking for coefficient of friction, not radius. Easy switch. I'll just put r over here and put mu there. Now we're good. Okay, same manipulation. All right, so our radius was 100 meters, okay, times 9.81. That'll give us our coefficient of friction. Okay, so that number there, squared divided by 981. Okay, so we are looking at a coefficient of friction of 0.710, actually 710, because we have 3 significant digits in that question. So 710 would be our coefficient of friction. No units on that. Okay, questions there? All right, so are the unbanked curve ones pretty much all the same? Okay, set friction equals centripetal force and off you go. All right, I want you guys to do a banked curve one. Unbanked. No. Oh, come on, I got a bank curve one in there somewhere. There we go. All right, I want you to try that one. Unbanked, or sorry, that is a banked corner. Okay, because obviously you're given an angle in this one. Okay, I'll give you a couple minutes on that one. So right away they tell me that it is a banked curve because they tell me that the banking angle is 20 degrees. Okay, so right off the bat I can write that I know I will be using this formula. The tan of theta is v squared over r times g, our banked curve formula. Okay, the givens that I have the radius, 125 meters, okay, and I know that theta is 20 degrees. All right, so I am looking for v in this question. So I want to multiply both sides by r times g. So I will have the tan of theta times r times g equals v if I square root that whole side. All right, so that'll look like this. The tan of 20 degrees times 125 times 9.81. Okay, and that should come out to 21.1 meters per second. Okay, everybody all right with that? Okay. Pretty straightforward question. In fact, these ones are even easier than the unbanked curves because you know you don't have to set it equal to anything. You just, here's my formula and I just plug it in. All right, so bank curve questions are pretty straightforward. All right, see if you can do that one. Looking for the bank angle on that one. So again, a pretty easy manipulation. We know that it's a bank curve, so we know we're starting out tan of theta equals v squared over r times g. So to find theta, I just have to do inverse tan. All right, so the inverse tan of 90 squared divided by 745 times 9.81, okay, and we get that this would have to be banked at 47.9 degrees. Okay, that is ridiculous. Okay, it is a hugely banked angle, but it is also really, really fast. Okay, because it does actually define it as a racetrack earlier in the question. Okay, so context matters, right? If this had been an exit ramp, okay, or an on ramp, that number would be unreasonable. Okay, nobody would ever bank an on ramp at 47 degrees. But for a racetrack, that's not unreasonable. Okay, cars go a lot faster. Okay, any questions on that stuff there? Okay, so you've got in your digital workbook some questions to do with this stuff. We probably won't do those today. We're going to talk a little bit about some other stuff. But when we come back, we'll probably do a few just to kind of refresh our memory of unbanked and banked curves and kind of things like that. All right. What I want to have a look at rest of the day here is artificial gravity. All right. So the process of theoretically producing it, because we don't have any spacecraft currently that actually do this. Right? We know it's super easy to do, okay? Well, theoretically easy to do, okay? Practically to do is a bit more complex, okay? Funny, right? Look at what it says on the can. It's a terrible one, actually, but I love the far side. Okay. All right. Now, what's the purpose of generating artificial gravity? Like, why wouldn't we just, like, for let's say example, like the Martian movie there? Hey, why wouldn't we just travel in zero gravity all the way to Mars? Seems like that would be the more fun way to go. Is there any reason why it seems like we have to be able to do that?
Astronauts muscles and stuff like that will weaken if they don't have gravity.
Yeah, that's one of many things that will happen to them. Your muscles will atrophy, right? You don't use it, you lose it. Okay? So if you're not using your muscles all the time, they can atrophy, and then you'll be very weak. Now, people will often say, well, gravity on Mars is 1/3 of that of Earth, so what's the big deal? Well, it's not so much your muscle weakness. That can be a problem for sure, okay? But you're eventually coming back to Earth at some point, and I think you'd probably like to be able to breathe. Okay? You use your muscles to breathe. Okay? When you inhale, okay, there are muscles that contract and bring your rib cage up. Okay? Your intercostal muscles. Okay? You also have a big muscle at the base of your lungs, okay, called your diaphragm. Okay? That contracts and flattens. Those things all the time are working in 1G. They work against the weight of your rib cage and things like that. You go into zero gravity, those muscles don't have to work at all. Lifting your weightless rib cage is no task, so they get weak. Same with your heart. Okay? Your heart's just a big muscle. And if it's pumping weightless blood, it doesn't have to work very hard. Okay? It's going to atrophy. That can be a problem long term. But that's only one in a list of many things that go wrong with your body in prolonged zero gravity. Okay, have you guys seen that new commercial that Chris Hadfield is in for like the optical topography coherence? The big joke is nobody can pronounce what the test is called. Okay, you guys haven't seen that yet? Yeah, he's in a new ad about some sort of eye test. Okay, his research in space when he was on the International Space Station was actually about space blindness. Zero gravity can permanently change the shape of your eye and cause space blindness. Okay? If you are in space for too long, and we're talking here like more than a year, okay? Even at a year, there's actually significant decrease in your visual acuity. Okay? You can start to really lose your vision. because most of the time your eyes are subjected to gravity, and so they stay a certain shape. But at zero gravity, they start to flatten, okay? And that can really affect your visual acuity, okay? In addition to a host of other problems. Okay, so some of those problems, okay, are on this diagram here. If you're not using your muscles, they atrophy. Your muscles are made of certain, compounds, materials. Those end up having to be filtered out by your kidneys and your liver, and that's hard for them. Okay, but even more than that are your bones. Okay, if you're like an elderly person, so like me, okay, you have to make sure that you keep your bone density up. Okay, you ever seen like a really old person, so like someone older than me, okay, and they kind of get like hunched, they get like a hunched back and whatever. That's from their bones losing bone density. It's called osteoporosis. Okay, it really affects elderly people. The best way to prevent osteoporosis is to simply walk around. Lift light things, okay, here and there. Like even those little tiny weights that look like a joke, okay? Even just doing that is enough to cause small microfractures in your bones. Okay? We do that all the time. It's perfectly healthy. Okay? Every time you make a small microfracture in your bone, it heals back stronger. But if you're in zero gravity, you never do that. And so your body, which is the ultimate recycler, starts to pull calcium and other minerals out of your bones, and your bone density goes way down. Okay? Chris Hadfield, when he was on the International Space Station, he worked out every day on what they call the Terminator. Okay? Treadmill number 2, T2. Okay? And they would have to be strapped onto this treadmill by a bungee cord, okay? Like a thing wrapped around their waist or vest, okay? And then they would try and run, right? But it's the next best thing, because it's really hard to run in zero gravity on a treadmill, because you kind of fly off of it every time. So that was one of the things, and they would do weights, obviously not weights, but like a Bowflex kind of a machine, okay, where they would have to push and use their bones, and his bone density still significantly decreased while he was on the International Space Station. Okay? By the time he got back, his bone density was that of a person 20 years older than he was. Okay? So zero gravity is really hard on the human body. And one of the things that can happen as your bone atrophies, okay, is the calcium it's made of has to be filtered out. Well, if you've suddenly got a lot more calcium in your blood than you're supposed to, it can lead to kidney stones. Kidney stones on Earth are acutely painful and sometimes a medical problem, okay? Because it's a sharp little jagged rock that has to come out of you, okay, through your ureter and your urethra and all of that. So it's got to exit the kidney, okay, go through the ureter, okay, then go into your urinary tract and come out the urethra. All along the way, that jagged little rock can cut up that urinary tract, okay, which can lead to a urinary tract infection. On Earth, you take antibiotics and you'll get better. If you're millions of kilometers from a hospital, that's much more of a medical problem than it is on Earth, where it's just an inconvenience and it's uncomfortable. Okay? Far from a hospital, that could be fatal. Okay? So there's all of these little things that they have to consider. Okay? Another thing that happens is your balance center completely changes. Okay? On Earth, in regular gravity, our ears, okay, the middle ear tells us about our orientation. If we're right side up, upside down, okay, if we like lean to one side, the ear detects that and the brain automatically tenses the muscles on the other side of the body to keep you from falling. In space, that doesn't work at all because there's no gravity to tell your middle ear which way is up and down, right? And for the first few days in zero gravity, astronauts are quite nauseous because their middle ear is constantly screaming at the brain, you're upside down, you're right side up, you're falling, you're leaning, and the brain is just like, oh my God, I feel so sick. Until finally the brain just goes, shut up. I am not listening to you anymore. And it just completely cuts off and doesn't listen to the middle ear for balance. Instead, it switches to the eyes, okay? Which is fine in zero gravity, right? On the International Space Station, there isn't really a floor and a ceiling and an up and a down. Everything is a wall and it all works the same, okay? So I look that way, that's up. Okay, I look that way, that's up. It doesn't really matter, okay, because there's no real up or down. The problem is when you return to gravity. In zero gravity, turning, your eye says, oh, okay, we're going over there, and your body just turns that way. But when you come back to gravity, it makes you clumsy. Okay? It's why you see astronauts being led away from their landing vehicle by 2 people, 1 on each arm. Okay? Because if you like shout to them, "Hey, Chris," and he looks like this, he'll fall over. Because his brain is trusting his eyes to tell him about his orientation. So he turns and looks like this, and the whole body just goes, "Oh, that way? Okay," and falls over. All right? So can you imagine you spent, 6 months in 0 gravity going to Mars. You're going to be the Neil Armstrong of Mars. You are going to put the first footprint on Mars and say something really important when you get to the bottom of the ladder. Except you get to the top of the ladder, look down, and your brain goes, "Okay," boom, 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 down the stairs. You crack your faceplate on the rock, and the first words are on Mars are, "Oh, died." Okay, that would be somewhat unceremonious. Okay, so it's a really big deal in terms of balance. Okay, so that can be a really big deal. It does take them quite a while when they return to Earth to regain that after being in 0 gravity for significant periods of time. In fact, they get really used to 0 gravity. Okay, show you a video. Okay, is that you have some part of the ship, if not, maybe the whole ship is just a big cylinder, okay, that is going to spin and rotate. Okay? As it spins, if you're standing right here, your inertia wants you to go in a straight line, according to Newton's first law. But since you're on the inside of this spinning drum, you push on the inside of that drum because of your inertia, okay, which creates a normal force. And that normal force feels just like normal force on Earth. The floor pushing back on my feet. It feels like gravity. Okay? It works just like gravity, as long as I'm in contact with the floor. If I jump, what'll happen? Okay? Well, if I'm moving around and around in a circle, then I've got some motion that I don't detect because I'm moving with this thing. But if I jump, I might be able to do this and end up on the other side. Okay? Because I'd follow an arc. Okay? I'd still have like that kind of projectile thing just because of the motion that I would have, but I could probably easily jump from one side to the other. The only problem is I'd have to land on my hands on the other side. Okay? I wouldn't be able to contort my body necessarily to face my feet down on the other side because there'd be nothing to push against as I'm flying through the air. Okay? It's kind of a strange sensation, but that's exactly how you do it. All you do is make this thing spin so that you get this desire to leave by your inertia, and the floor pushes back to prevent it, and you feel like you have actual weight. The nice thing about this is you can change how you feel. All you have to do is change the rate it spins at. If you make it spin faster, you feel heavier. All right? You probably want to do that like on your way back. If you've gone to Mars, you're going to want to maybe use a little heavier gravity on the way back, so you can get nice and jacked. Okay, before you get back, because suddenly everything's so much heavier. Okay, look good for all the pictures when you get home. Right? Whereas on the way to Mars, you probably would want to slowly back the gravity off so you could get used to what Martian gravity would feel like, so you don't fall and hurt yourself or break your faceplate or something like that when you get to Mars, because you're used to 1G and suddenly it's 0.3G. Okay? You move a lot differently. Okay? If you've ever seen videos of the astronauts on the moon, they actually had to scoot along on the moon, because if they walked normally, like we always press up a little bit when we walk, they would actually come off the surface, and it was a concern that they might fall and break their faceplate and then die. Okay, so they actually shuffled a little bit. Okay? They actually had one shot of one of the astronauts, and he just jumped straight up in the air in his suit, which is heavy. Okay? But because he was on the moon, he looked like an incredible athlete. Okay? Because he was able to jump in this spacesuit, like really high off the surface, and then came back down. Okay? Just because they weigh on the moon 1/6 of what they would weigh here. Okay, so, all right. So this idea here has been around for a very long, long time. Okay? And it's what the gravitron, okay, that ride that we talked about the other day, is designed around. So I actually got some videos of that as well.